So from the expression of gravitational potential, phi equals to minus g m over r, we notice that there is a series of equipotential surfaces which are imaginary spherical shells centered at the Earth's center. Since the gravitational potential phi only depends on r, the potential on each of these shells is going to be a constant value. All right, and the potential increases as we go further and further away from the Earth, which means that the outer shells have a higher potential than the inner shells. Okay, in other words, if you want to go from, let's say, this shell to this shell, you will need to find a way to increase the gravitational potential energy of the object. So this idea is related to the idea of escape speed. Okay, so what's the escape speed? It is the minimum speed at which a body can be projected from the surface of the planet so that it reaches an infinite distance from the planet. Right? So the idea is this, right? The surface of the planet, the object has a certain potential energy, and this potential energy is negative. So how much energy do we need to supply to this spaceship so that it can go all the way to infinity? And at infinity, the potential energy is 0. Alright, so how much energy do we need? So in other words, we just have to find what is the difference in the potential energy from the surface of the planet to infinity, where u equals to 0. Okay, so we can use conservation of energy, right? So where does the GP comes from? Right, it comes from the KE, right? The loss in the KE will be converted to the gain in the GPE. Okay, so we put in the values, right? So VI is the escape speed. Okay, and we assume that the spaceship, when it reaches infinity, it will just come to rest. Okay, so that's why the final KE is 0. Right? And on the right hand side, you have the change in GPE. Okay, which is the final GPE 0 minus the initial GPE, which is the GPE on the surface of the Earth. So after some mathematical manipulations, you'll find the expression for the escape speed. Alright, and this escape speed is the same regardless of the mass of the objects. Let's look at example 6 to see how we apply the formula. We want to calculate the escape speed from Earth for a 5,000 kg spacecraft and determine its kinetic energy. Okay, so substituting in the values, we find that the escape speed is about 1.1 times 10 to the power 4 meter per second. Okay, notice that this escape speed is independent of the mass of the object. Okay, so it doesn't matter whether the spaceship is 5,000 kg or 1,000 kg. You will have to ensure that the spacecraft has the same has a minimum of this speed before it can escape from the Earth. Okay, but the kinetic energy required does depend on the mass, right? Because it's half mv squared. And after putting in the numbers, you find that it is a huge amount of energy that is required. One of the very interesting phenomena that we can also analyze using the idea of escape speed is the phenomenon of black holes. So what is a black hole? It's just a region of space where the pull of gravity is so strong that nothing can escape from it, including light. So if you can find a region in space, okay, whereby the escape speed is greater than the speed of light, 3 times 10 to the power of 8 meter per second, then this region of space will appear black, right? Because you can't, there's no light. Why is it called a black hole? Because no light can escape from it. Okay, so how are black holes form? Okay, just some general knowledge. Okay, so it's born from stars, right? So if the star has a low to average mass, like our own star in the solar system, okay, it's considered a star that is not very massive. Okay, what happens is that when there is still enough fuel, it will keep on burning, right? And this pressure that's generated by the fuel will sustain the star and prevent it from collapsing. Once it has expended all its fuel, there's no more pressure, outward pressure due to the burning of the fuels, and the star will start to collapse under its own gravitational field. Okay, as in the you can imagine that the size so massive that everything on the surface of the star is being put towards the center of the star, so the star will start to collapse under its own weight. Now if the mass of the star is not too big, right, like just one solar mass similar to our star, our sun, it will collapse until the electrons in the atoms stop it from collapsing, right? Because the electron, the former term is called electron degeneracy pressure, right? Because electrons doesn't want to occupy the same space at the same time. Okay, so this outward pressure due to the electrons will stop the star from further collapsing, and the final state is known as a white dwarf. Okay, now what if the star is more massive? It's a large mass star. The electron degeneracy pressure is not enough to prevent it from collapsing. So the gravitational pull is so strong such that the electrons will collapse into the protons, into the nucleus. And what happens is that the electrons and the proton, okay, they will become nucleus. Not nucleus, neutrons. Okay, everything becomes a neutron, right? Because the charges, they neutralize one another, right? Electrons, protons, and so as a result, everything becomes so dense. Essentially, it's like a neutron, concentrated, the neutron, okay, neutrons together without any space between them, and we call this a neutron star. So what prevents it from collapsing is the neutron degeneracy pressure, because neutrons also don't like to be on top of one another, right? So there is some outward pressure that prevents the star from further collapsing. Now what happens if the mass of the star is so big, it's very very large, such that even the neutron degeneracy pressure cannot prevent it from collapsing even more? Then everything keeps on collapsing until it becomes a black hole. So it becomes something like a huge mass concentrated in a very small point, because nothing can stop it from collapsing. So it keep on collapsing until it reaches a very small point, and that is the black hole. Okay, so what is the size of the black hole? Well, the size of the black hole, usually we will use this the Schwarzschild radius as to give an indication of the size of the black hole. Essentially, it is the boundary whereby light cannot escape. Okay, so if let's say if you have a lot of mass that's concentrated in a very small space, right, then there you can find a imaginary sphere around this space, whereby if you put in the formula, if you put in the values in your escape speed formula, you'll be able to find that the even light cannot escape once you go beyond this point. Alright, so this is for those students who are interested to find out. You can go and find out. Let's say if you have got the sun, okay, our own sun, if you can find out the mass of our sun, and then try to find out how big is the Schwarzschild radius, which is like how big is, if let's say the sun collapses into a singularity, right? What is the radius of this imaginary sphere whereby light cannot escape? In other words, the escape speed of this imaginary sphere on the surface of this sphere is equal to the speed of light. All right.